Hello, and welcome. In this video, we're going to explore three fundamental concepts in linear algebra that are deeply interconnected. By the end of this lesson, you will be able to solve matrix equations of the form AX equals B, understand and solve homogeneous systems, and determine if a set of vectors is linearly independent. These ideas are the building blocks for much of what you'll do in linear algebra, so let's get started. First up, let's tackle matrix equations. Our goal here is to learn how to solve equations that look like this. AX equals B. Here, A is a matrix, X is a vector of unknown variables, and B is a known vector. Our job is to find the vector X. Let's start with the simplest case, when the matrix A is invertible. This means A is a square matrix and has a non-zero determinant. If A is invertible, the solution is straightforward. We can multiply both sides of the equation by the inverse of A, which we write as A inverse. So we get A inverse times AX equals A inverse times B. Since A inverse times A is the identity matrix I, we are left with X equals A inverse times B. This gives us a unique solution. Let's see this in action with an example. Suppose we want to solve the equation. The matrix 2, 1, 3, 2 times the vector x1, x2 equals the vector 4, 7. First, we need to find the inverse of our matrix A. For a 2 by 2 matrix, the inverse is 1 over the determinant times the adjoint matrix. The determinant of A is 2 times 2 minus 1 times 3, which is 4 minus 3, or 1. The adjoint matrix is found by swapping the diagonal elements and negating the off-diagonal elements. So A inverse is 1 over 1 times the matrix, 2 minus 1 minus 3, 2. Now we can find our solution vector X by multiplying A dash inverse by B. X equals the matrix 2 minus 1 minus 3, 2 times the vector 4, 7. This gives us the vector 2 times 4 minus 1 times 7, and minus 3 times 4 plus 2 times 7. Calculating this, we get 8 minus 7 and minus 12 plus 14, which simplifies to the vector 1, 2. So our solution is x1 equals 1 and x2 equals 2. This method works perfectly when A is invertible, but what if it's not? We'll explore that next. Now let's consider the case where the matrix A is not invertible. This means its determinant is 0 and it doesn't have an inverse. In this situation, we can't use the inverse method. Instead, we use a technique called Gaussian elimination. The process involves creating an augmented matrix by placing the matrix A and the vector B side by side, separated by a line. Then, we use elementary row operations to transform the matrix A into row echelon form. This process will reveal whether a solution exists and, if so, what it is. Let's work through an example. Consider the equation. The matrix 1, 2, 3, 2, 5, 3, 1, 0, 8 times the vector x1, x2, x3 equals the vector 1, 6, minus 6. First, we form the augmented matrix. This gives us the matrix 1, 2, 3, 1, 2, 5, 3, 6, 1, 0, 8, minus 6. Now we perform row operations to get it into row echelon form. Let's start by making the elements below the first pivot, which is 1, equal to 0. We'll replace row 2 with row 2 minus 2 times row 1, and replace row 3 with row 3 minus row 1. This gives us the new matrix 1, 2, 3, 1, 0, 1, minus 3, 4, 0, minus 2, 5, minus 7. Next, we'll make the element below the second pivot, which is 1, equal to 0. We'll replace row 3 with row 3 plus 2 times row 2. This results in the matrix 1, 2, 3, 1, 0, 1, minus 3, 4, 0, 0, minus 1, 1. Now the matrix is in row echelon form. We can convert it back into a system of equations and solve using back substitution. The last row tells us that negative x3 equals 1, so x3 equals negative 1. The second row tells us x2 minus 3 times 3 equals 4. Substituting x3, we get x2 plus 3 equals 4, so x2 equals 1, The first row tells us x1 plus 2 by 2 plus 3 times 3 equals 1. Substituting x2 and x3, we get x1 plus 2 minus 3 equals 1, which means x1 minus 1 equals 1, so x1 equals 2. So the unique solution is the vector 2, 1, minus 1. Let's do one more example of solving ax equals b using Gaussian elimination, but this time we'll see a case with infinitely many solutions. Consider the equation. The matrix 1, 2, 3, 2, 4, 6, 3, 6, 9 times the vector x1, x2, x3 equals the vector 1, 2, 3. Notice that the second row of matrix A is just 2 times the first row, and the third row is 3 times the first row. This tells us the matrix is not invertible. Let's form the augmented matrix and perform row operations. The augmented matrix is 1, 2, 3, 1, 2, 4, 6, 2, 3, 6, 9, 3. We'll replace row 2 with row 2 minus 2 times row 1, and row 3 with row 3 minus 3 times row 1. This gives us the matrix 1, 2, 3, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. The last 2 rows are all zeros. This indicates that we have infinitely many solutions. The first row gives us the equation x1 plus 2 by 2 plus 3 times 3 equals 1. We have one equation, but 3 variables. This means we can choose 2 of the variables freely. Let's call them free variables. Let's set x2 equal to a parameter s and x3 equal to a parameter t. Now we can express x1 in terms of s and t. x1 equals 1 minus 2's minus 3t. We can write the general solution vector x in terms of these parameters. The vector x is 1 minus 2's minus 3t s t. We can also decompose this into a particular solution and a linear combination of vectors from the homogeneous system. This is the vector 1, 0, 0 plus s times the vector minus 2, 1, 0 plus t times the vector minus 3, 0, 1. This is the general solution. So we've seen how to solve ax equals b using Gaussian elimination, which works for all cases, including when there are infinitely many solutions. Next, let's dive into a special type of matrix equation called a homogeneous system. A homogeneous system is any system of linear equations that can be written in the form ax equals 0, where 0 is the zero vector. The key thing to notice about homogeneous systems is that they always have at least one solution. This solution is the zero vector itself, where all variables are 0. We call this the trivial solution. The interesting question is whether there are any other solutions, called non-trivial solutions. A non-trivial solution is any solution vector x that is not the zero vector. A homogeneous system has non-trivial solutions if and only if the matrix A is not invertible. In other words, if the determinant of A is 0. Let's find the solutions to a homogeneous system. Consider the system. The matrix 1, 2, 3, 2, 4, 6, 3, 6, 9 times the vector x1, x2, x3 equals the zero vector. We've seen this matrix before. It's not invertible. Let's use Gaussian elimination. The augmented matrix is 1, 2, 3, 0, 2, 4, 6, 0, 3, 6, 9, 0. Performing the same row operations as before, we get the matrix 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0. This gives us the single equation x1 plus 2 by 2 plus 3 times 3 equals 0. Again, we have 2 free variables. Let x2 equal s and x3 equal t. Then x1 equals negative 2's minus 3t. The general solution vector x can be written as a linear combination of 2 vectors. X equals s times the vector minus 2, 1, 0, plus t times the vector minus 3, 0, 1. These 2 vectors, minus 2, 1, 0, and minus 3, 0, 1, are called basis vectors for the null space of A. The null space is the set of all solutions to AX equals 0. Let's look at another homogeneous system example. Solve the system. The matrix 1, 1, 2, 2, 3, 3, 3, 4, 5 times the vector x1, x2, x3 equals the 0 vector. We'll form the augmented matrix and use Gaussian elimination. The augmented matrix is 1, 1, 2, 0, 2, 3, 3, 0, 3, 4, 5, 0. First, we'll replace row 2 with row 2 minus 2 times row 1, and row 3 with row 3 minus 3 times row 1. This gives us 1, 1, 2, 0, 0, 1, minus 1, 0, 0, 1, minus 1, 0. Next, we'll replace row 3 with row 3 minus row 2. This results in 1, 1, 2, 0, 0, 1, minus 1, 0, 0, 0, 0, 0. We have one free variable. Let's set x3 equal to a parameter s. From the second row, x2 minus x3 equals 0, so x2 equals x3, which is s. From the first row, x1 plus x2 plus 2 times 3 equals 0. Substituting, we get x1 plus s plus 2 equals 0, so x1 equals negative 3s. The general solution is x equals s times the vector minus 3, 1, 1. This vector is a basis for the null space. Finally, let's see a case with only the trivial solution. Solve the system. The matrix 1, 2, 3, 4 times the vector x1, x2 equals the 0 vector. The determinant of A is 1 times 4 minus 2 times 3, which is 4 minus 6, or negative 2. Since the determinant is not 0, we expect only the trivial solution. Let's confirm with Gaussian elimination. The augmented matrix is 1, 2, 0, 3, 4, 0. Replace row 2 with row 2 minus 3 times row 1. This gives 1, 2, 0, 0, minus 2, 0. From the second row, negative 2 times 2 equals 0, so x2 equals 0. From the first row, x1 plus 2 times 2 equals 0. Substituting x2, we get x1 equals 0. The only solution is the trivial solution, x equals the 0 vector. Our final topic is linear independence. This is a crucial concept that helps us understand the structure of vector spaces. A set of vectors, v1 through vp, is said to be linearly independent if the only solution to the vector equation c1v1 plus c2v2 plus cpvp equals the 0 vector is the trivial solution, where all the scalar coefficients c are 0. If there is a non-trivial solution, meaning at least one of the c's is not 0, then the vectors are linearly dependent. This means that at least one vector can be written as a linear combination of the others. It's redundant. How do we test for linear independence? We can form a matrix A whose columns are the vectors we're testing. The vector equation c1v1 plus cpvp equals 0 is equivalent to the matrix equation AC equals 0, where c is the vector of coefficients. So testing for linear independence is the same as solving a homogeneous system. The vectors are linearly independent if and only if the system AC equals 0 has only the trivial solution. A quick way to check this is to find the rank of the matrix A. The vectors are linearly independent if and only if the rank of A is equal to the number of vectors. Page. The rank is the number of non-zero rows in the row echelon form of A. Let's try an example. Are the vectors v1 equals 1, 2, 3, v2 equals 2, 5, 3, and v3 equals 1, 0, 8 linearly independent? We form the matrix A with these vectors as columns. A equals the matrix 1, 2, 1, 2, 5, 0, 3, 3, 8. Now we find the rank of A by reducing it to row echelon form. We'll replace row 2 with row 2 minus 2 times row 1, and row 3 with row 3 minus 3 times row 1. Next, replace row 3 with row 3 plus 3 times row 2. The matrix is in row echelon form. It has 3 non-zero rows, so its rank is 3. Since the rank of A, which is 3, equals the number of vectors we started with, which is also 3, the vectors are linearly independent. Let's do another example, this time with a set of vectors that are linearly dependent. Are the vectors v1 equals 1, 2, 3, v2 equals 2, 4, 6, and v3 equals 3, 6, 9 linearly independent? Again, we form the matrix A with these vectors as columns. A equals the matrix 1, 2, 3, 2, 4, 6, 3, 6, 9. We've seen this matrix before. Let's reduce it to row echelon form. After performing the row operations, we get the matrix 1, 2, 3, 0, 0, 0, 0, 0. This matrix has only one non-zero row, so its rank is 1. The rank of A is 1, but the number of vectors, P, is 3. Since the rank is less than the number of vectors, the vectors are linearly dependent. This means we can find a non-trivial linear combination that equals a zero vector. In this case, we can see that v2 is 2 times version 1, and v3 is 3 times version 1. So 2v1 minus v2 equals the zero vector. This is a non-trivial solution, confirming linear dependence. Let's do one final example. Are the vectors v1 equals 1, 0, 0, v2 equals 0, 1, 0, and v3 equals 0, 0, 1 linearly independent? These are the standard basis vectors for R3. Let's form the matrix A. A equals the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. This matrix is already in row echelon form. It has 3 non-zero rows, so its rank is 3. Since the rank of A, which is 3, equals the number of vectors, P, which is also 3, the vectors are linearly independent. This makes sense, as you can't form any of these vectors by combining the others. Let's quickly recap what we've covered today. First, we learned how to solve matrix equations AX equals B. If A is invertible, the solution is unique and given by X equals A dash inverse B. If A is not invertible, we use Gaussian elimination on the augmented matrix A to find either a unique solution, infinitely many solutions, or no solution. Second, we explored homogeneous systems. AX equals 0. These always have the trivial solution, x equals 0. They have non-trivial solutions, if and only if A is not invertible, which we find using Gaussian elimination to identify free variables and basis vectors for the null space. Finally, we defined linear independence. A set of vectors is linearly independent if the only way to combine them to get the zero vector is by using all zero coefficients. We test this by forming a matrix A with the vectors as columns and checking if the rank of A equals the number of vectors. These three concepts are fundamental to linear algebra. Understanding them will allow you to solve a wide variety of problems and build a strong foundation for more advanced topics. Thank you for watching.